Many thanks to the organisers for putting together this really interesting programme and for inviting me to give a talk. I personally did my Masters in High Energy. Now I'm in the NAS department and working on condensed matter, so I have some non-trivial intersection with all three areas. Today I will discuss these works, written by my fantastic supervisor in Oxford, Sakura Shapiro-Namiki, along with various subsets of Laksha Bhardwaj, Lea Bhattini, Daniel Pager, Apurv Tiwari, and myself. They cover the categorical Landau paradigm for gapped phases, subsequently extended to gapless phases, both in the SymTFT framework and with concrete lattice model realizations. This last work was written in collaboration with Fan Yang and Hannes Pichler in Innsbruck, who work on cold atom quantum simulators. These are some of many related works on the SymTFT, both from high energy physics and condensed matter literature, on gapped phases and anomalies, gapless phases, including intrinsically gapless phases, which I will discuss, and many works on lattice models, various types of dualities, of anomalies, and many realizations of gapped and gapless phases, including with Hagerup symmetry and with applications to quantum computation for some models based on RAPI-8, for example. So we see that this is clearly a very interdisciplinary field with far-ranging works. My aim will be to discuss the categorical Landau paradigm, which classifies phases in 1+1D described by a generalized symmetry. This is encoded in a fusion category S, and the main tool I will use is the SymTFT, whose bulk comprises of topological defects in the Drinfeld center of the fusion category. Physically, these are anyons because since this is in one extra dimension, so in 2+1D, these can have any spin. The SymTFT has two boundaries, the symmetry boundary, which fixes the symmetry of our theory, and the physical boundary encoding its dynamics. And then we can get back T with symmetry S by shrinking the topological SymTFT slab. I will also discuss 1+1D lattice models, including simple spin chain realizations, which can be realized in quantum simulators. So I will focus on 1+1D, but as we heard yesterday and in various related talks, the SymTFT is very powerful in general and can be applied to higher dimensions and to different contexts. So in the SymTFT framework, gapped and gapless phases with categorical symmetry S are described by anion condensation of the SymTFT boundaries. So, as was remarked yesterday, this anion condensation has slightly different, different meaning to the word condensation in high energy theory. So here, a condensable algebra of anions is formed by bosons, which are also mutually local among them. So they have no braiding signs. This means that they can be condensed, so they can end on a symmetry boundary and become trivial. So we fix the symmetry boundary of the SymTFT by picking a maximal set of such anyons, and then the ones that are not in this algebra, but the braid non-trivially, would then project and generate our symmetry. Then once we fix the symmetry, we can change the physical boundary of the SymTFT and get various gapped and gapless phases. The gapped phases are obtained by picking a maximal algebra here, whereas the gapless ones are obtained by performing a non-maximal anion condensation and will give us an interface between Z of S, our starting topological order, and the reduced one, Z of S prime. One feature of gapped phases is the number and type of local operators. So local operators in the theory, in the 1+1D theory, come from SymTFT anyons that can end on both the symmetry and the physical boundary. The identity anion is always one of these, which will give us the identity local operator. If this is the only anion that can end on both boundaries, we will have a unique ground state invariant under the full symmetry. This is therefore an SPT phase, and it can be trivial or non-trivial, even for these generalized symmetries. And these different types of SPT phases can be detected by string order parameters, as we'll see in some examples. And the string order parameters come from the SymTFT, and they are given by anyons, which can end on B-Phys, but not on B-Sym. So we will have a local operator after shrinking the slab here attached to a symmetry line. If such string order parameter has a non-zero vacuum expectation value, we will have a non-trivial SPT, and we will see examples of this. If instead we have multiple local operators coming from multiple anyons and being on both boundaries, the non-identity ones will be charged under certain subsymmetries. Therefore, by taking linear combinations of these local operators and constructing idempotents, we will have ground states which are related to each other by spontaneously broken generators in our symmetry category. So this is a very general framework to classify these phases with any categorical symmetry. If instead we perform a non-maximal anion condensation, described by a non-maximal condensable algebra A, we will have this interface IA between our starting Z of S and this reduced topological order Z of S prime, which is the mathematically Drinfeld center of a smaller fusion category S prime. The anyons which are condensed are the ones that can end on this interface, and as we said before, they have to be all bosons and have trivial mutual braiding. This is because they become the identity anion in Z of S prime. Therefore, if we have some anyons which are non-local with the ones in our algebra, i.e. they have some non-trivial braiding, these must be confined to this interface. They cannot go through, because if they did, they would have some non-trivial braiding with the identity, which is clearly inconsistent. So we have some confined anyons, whereas the ones which are local with the algebra, so which have trivial braiding, can consistently go through and become mapped to an anion A prime in Z of S prime. So what's important is that this reduced topological order and the whole map of generalized charges can be computed from the SymTFT, and is very useful because we can, if we consider a CFT for S prime symmetry between two S prime gap phases, for example, the easing CFT between the Z2 trivial and Z2 SSB phase, we can then use this map of topological operators to view this as an S-symmetric CFT, to obtain an S-symmetric CFT from it. So in examples, we will see S prime is, as I said, very simple. It's Z2, and we have the easing CFT, but then we will get some S-symmetric CFTs where S is a much more complicated fusion category, for example, REP8, which is non-invertible. Oh, sorry. Once we have all these condensable algebras, we can arrange them into a phase diagram determined by inclusion of algebras, which physically corresponds to possible deformations of these. At the lowest level, we have the gapped phases, while at higher level, the gapless ones. And from here, we can read off which phases are intrinsically gapless, i.e. phases whose gaplessness is protected by the symmetry. These are phases which exhibit some symmetry properties which are, as I said, which protect their gaplessness, because they can only be deformed by spontaneously breaking some symmetry. In particular, an IGSPT fully preserves the fusion category symmetry, but it can only be deformed to an SSB, which at least partially breaks it. Whereas an IGSSB is a gapless phase which already exhibits a certain degree of spontaneous symmetry breaking, but it can only be gapped to an SSB with a greater degree of symmetry breaking, measured, for example, by the number of local operators. Let's come to an example given by the fusion category REP8 of representations of the dihedral group of order 8 of symmetries of a square. We can present it as Z2, semi-direct Z2, where we label the two Z2 factors in a normal subgroup as A and B, which are exchanged by C. And the reason we chose this group is that this Z2, semi-direct Z2 structure means that we can realize it on the lattice as a tensor product Hilbert space based on qubits. But the non-invertible, the non-abelian nature of the 8 means that we will have a two-dimensional irrep E, which obeys non-invertible fusion. So these are the irreducible representations of the 8, which we will choose as our symmetry category. We have 4 one-dimensional irreps, which form Z2. So 1C times 1A is 1CA. And this two-dimensional E, which fuses to the sum of the 4 one-dimensional irreps. Now, the anyons in the SymTFT are labeled by conjugacy classes of G and representations of the centralizer. So if we want the symmetry to be generated by the representations, we have to condense the conjugacy classes. So this is the symmetry algebra for Rep8, which shows us that these anyons become trivial. And once we fix the symmetry algebra, by then choosing as the physical boundary of the SymTFT all the possible condensable algebras, we will get all gapped and gapless spaces. There are 38 of them, which can be arranged into this phase diagram. And I will now zoom into these two colored areas for the examples of GSPTs and GSSBs. Now, as we said before, a GSPT phase fully preserves the symmetry, and we can determine its properties by choosing the condensable algebra and then computing from the SymTFT the reduced topological order and the map of generalized charges. For example, if we choose this algebra labeled a GSPT, the reduced topological order is the toric code, so the center of Z2. And this has two gapped boundary conditions, electric and magnetic, which means that this gapless space corresponding to it can be deformed to an SPT if here we choose the magnetic boundary, or an SSB if we choose the electric one. And what is this gapless space? Well, since this is Z2 reduced order, we can input the Ising CFT, and then from the map of generalized charges, we again get the Ising CFT, where here the Z2 is realized in terms of Rep8. What type of SPT is this? Of SSB is this? As I said, if we choose the electric boundary, we get this phase with an order parameter given by AB, which is charged under the non-invertible symmetry here depicted in blue. So this is completely invariant under the Z2 one-dimensional irreps, green and red, generated by the green and red. But the two vacua are exchanged by the two-dimensional E irrep. If instead we choose this other algebra labeled by AI GSPT, we have a different reduced topological order, which is the double Senion model, or mathematically the center of Z2 with a free co-cycle anomaly, which is non-trivial on it. So in this case, AB becomes, which is a boson, obviously becomes again a boson, SS bar. But this time, because of the anomaly, we only have one gapped boundary condition, which is an SSB phase, this one. So we see that in this case, that this is a standard GSPT because it can be deformed to an SPT of the same symmetry properties, while this is an IGSPT because it can only be gapped to a phase that breaks in symmetry. This can be repeated, this analysis can be repeated and extended to all the other algebras. And in particular, these are examples of GSSBs, so gapless phases which exhibit already some degree of symmetry breaking. For both of these, the reduced topological order is again the toric code, so they can be deformed to two gapped phases. Again, we input the Ising CFT, and in this case, we get this Z2 GSSB with two copies of Ising, which are exchanged by this red invertible Z2 symmetry. Now, notice here that the blue non-invertible symmetry E is partially broken because it sends each Ising to a sum of both. So Ising plus goes to Ising minus, but also to Ising plus, so it's partially broken. This GSSB can be deformed to a gapped SSB, which has the same symmetry properties. But it can also be deformed to this other phase, in which the non-invertible blue symmetry is completely broken. So what happens is Ising plus and Ising minus each split into two Z2 orbits, exchanged by this red symmetry, as these two were. But this time, rather than being sent to the other Ising and itself, each vacua here is sent to a sum of two different ones. So in this phase, the non-invertible E is completely broken. Now, another very interesting gapless phase is this Ising IGSSB. Again, the reduced topological order is the toric code, so we can input Ising. And we get a gapless phase with three degenerate gapless universes. Ising 0 is invariant under the Z2 invertible symmetry, while Ising plus and Ising minus are exchanged by it. And furthermore, Ising 0 is sent to the sum of Ising plus and Ising minus, and vice versa, by the non-invertible symmetry. So we see that in this phase, we have these three copies of Ising, which are related to each other by the Ising fusion category. And this pattern of symmetry break-in isn't present in any gapped phase. So this is an intrinsically gapless SSB, which can only be deformed to SSBs with a greater number of vacua. again, from the SymTFT and the map of generalized charges, we can determine exactly how this symmetry gets further broken in the two gap faces. So in particular, in this case, what happens is this red symmetry of Ising 0 gets broken, and so Ising plus and Ising minus both go to a vacuum, exchanged by the red symmetry, whereas Ising 0 also splits into two brown states exchanged by the red symmetry. Instead, in this other case, Ising 0 remains invariant under the Z2, Z2 invertible symmetry, and it becomes this ground state 5, which is invariant under it. While Ising plus and Ising minus have this, are invariant under this green Z2 symmetry, which gets broken. So each copy of these two Isings gets split into two ground states exchanged by this green symmetry. So we see that in this phase, repliate is fully spontaneously broken. So we've seen that the categorical Landau paradigm is very general, and it enables us to get a lot of SymTFT, of predictions from the SymTFT on all the properties of these gapped and gapless phases. Now, can we test them with concrete 1 plus 1D Hamiltonians? In particular, can we also propose some models which could potentially be realized in quantum simulators? The answer is yes. So there's this very general construction called the anion chain, which gives Hamiltonians with any categorical symmetry S and takes as input a category C, a module category M. So what happens here is we have basically these elements of the module category and here in the morphism space arranged on a spatial circle. The Hamiltonian operator acts from above, whereas the symmetry ones act from below. But so in general, this is a constrained Hilbert space, but for certain models, like the one we studied with repliate symmetry, it simplifies to a spin chain on a tensor product Hilbert space based on qubits, where the operators in the Hamiltonians are simply can be written in terms of Pauli X and Z. So this is the setup. Basically, we take the 8 here to be this category C. So on each lattice site I, we can realize it in terms of these 3 qubits. Then, for the experimental proposal, at each site we have 3 Rydberg atoms, where each Rydberg atom has a hyperfine splitting between the 2 ground states. So these are basically degenerate. There's just a hyperfine splitting between them, but they are long-lived. So it's a very good simulation of a qubit. Whereas there's this Rydberg state, which can induce interactions between them. At each site, we have these 3 data qubits, and then between them, we have this ancilla qubit. Here we can have interactions between these, whereas the ancilla qubit enables us to realize interactions between neighboring lattice sites. Now, to simulate time evolution, given by e to the minus ith, we can discretize time, which is called a trotterization, and then apply on-site operators, and these can be done in parallel because they're all on independent sites, and then inter-site ones in 2 steps. Here, this is between I and I plus 1, this is between I and I minus 1, and simulate all these Hamiltonians. I mean, technically, not all of them immediately. I mean, this is very amenable to some of them, but it can possibly be generalized also to encompass all of them. Now, for the technical details, who's interested, we can we can realize these left and right multiplication operators, which are basically generalizations of Pauli X. So these are all written as Pauli X on each subsite, 1, 2, and 3. Notice here that LC, which swaps A and B, is X1 on the first qubit, and then swap 2 and 3, on which A and B are realized. The symmetry operators are instead diagonal and written in terms of Pauli Z, and here we have a more complicated expression for the 2-dimensional irrep E. And then for each subgroup of the 8 up to conjugacy and 2 cocycle beta, we can write a Hamiltonian realizing the gapped phase. This is repliate symmetric because we have this projector term, which is also diagonal, so obviously commutes with the diagonal symmetry operators. And this disorderin term, where we have multiplication by F and then F inverse. So since these symmetry operators act by basically picking out the matrix representation, and here we have F and F inverse, the matrices cancel, and so we have, this Hamiltonian is indeed repliate symmetric. There are 11 gapped phases with all these symmetry structures. There are 3 SPTs and 3 Z2 SSBs. This repliate mod Z2 Z2 SSB, where the invertible Z2 Z2 is preserved and this two-dimensional E swaps them. Then we have these Z2 Z2 SSB, so we have 2 copies of Z2, and in which the non-invertible symmetry is fully broken. And then finally this repliate SSB, where, as I said, we have this 5th ground state, which is invariant under the invertible symmetries, and then we have, a break-in of the other ones. Yeah. So, I mean, in this case, the full non-invertible, the full repliate symmetry is broken. Let's look at the SPTs more closely. So there's one which is given by this Hamiltonian, which is simply a projector onto the identity group element, which is realized as 0, 0, 0 on each lattice side. So here we simply have the tensor product of just zeros on all sides. So this is just completely trivial, and this is a trivial SPT. Instead, if we pick a Z2, Z2 subgroup with a non-trivial 2 co-cycle, we can get these types of Hamiltonians, which are still commuting projector Hamiltonians. So we can write the ground state. Here simply Z1 sets the first 2 bits to 0, then here we have X, so we can choose plus, and here again we have 0. And then we act on this with 1 plus this other operator. So this is the ground state, and which is unique for this Hamiltonian. It's fully repliate symmetric, but it has non-trivial entanglement. It can't be written as a tensor product. And, I mean, this is an indication it's a non-trivial SPT, and indeed, we can compute these string order parameters, which come from, as I said, the anyons in the SymTFT that can end on the physical boundary, but are attached to these symmetry strings. And in this lattice model, we can get them by taking these terms in the Hamiltonian and expanding these Z strings. So these have unit, so there are various string order parameters, and they have unit VAV in these non-trivial SPT phase, but they annihilate the trivial one. I mean, they have 0 expectation value in the trivial one. So this is another way to distinguish the trivial SPT from the other 2 non-trivial ones. So another interesting phase is this repliate SSB. It has 5 ground states. So the first one can simply be written as the tensor product of the superposition of all group elements with all plus signs. And then we can get the other ones by acting on this with the 4 non-trivial irraps. So we can get ground state 2 by acting with this invertible red irrap, ground state 3 by acting with the green one, ground state 4 with acting with the product, and ground state 5 by acting with the non-invertible blue operator, the symmetry operator SE. And we see indeed that it's non-invertible because if we act on GS5 with SE, we have here the fusion of SE with itself, which is the sum of the 4 one-dimensional irraps, so we get the sum of these other 4 ground states. Now, an interesting feature is that while these first 4 ground states, the ones associated to the one-dimensional irraps, are just tensor products of these superpositions with some minus signs for these other irraps, SE can't be written as a tensor product. It has non-trivial entanglement. And this is because for the one-dimensional irraps, what happens is the symmetry operator picks out basically the character of the group element, so the trace of the group elements in that representation, where the group element is given by the product along the circle. So for the one-dimensional irraps, the products of the characters is equal to the character of the product. So we start with a tensor product state, and we get tensor product states. Instead, for the 2-dimensional E, the character of the product is not the same as the product of the characters. So this gives us this entangled non-tensor product state. Finally, we can now take interpolations between these gapped Hamiltonians to study the critical points, the phase transitions between them. For example, this is a numerical plot between the Z2, SSB phase, which has 4 ground states. Here we see that they're all degenerates, whereas this purple one is the 5th one, which is higher in energy here. And then at the end of the interpolation, we get the repliate SSB, which has 5 degenerate ground states. Now, at the critical point, we have this easing IGSSB we discussed previously, we saw previously from the SymTFT. And indeed, using these Hamiltonians, we can really concretely test all the SymTFT predictions. And indeed, here we get this threefold degenerate space of ground states. And analytically, we can also see that it's basically the easing for this green symmetry, which is basically on the first qubit, times an SSB on the other 2 qubits. And numerically, we can also pick out all these different universes by adding a small symmetry breaking term. So if we add a small term which breaks this blue non-invertible symmetry, we can distinguish I0 and the sum of these two, and then we can distinguish these two by adding a small red symmetry breaking term. And so we can really introduce a fine split in between these and test all these symmetry properties, which are exactly the ones that the SymTFT predicted. Furthermore, since we gain, along this transition, we gain a new local order parameter, which then combines to give this new ground state. So, in conclusion, we've seen that the categorical Landau paradigm is very general and enables us to study and map out all these gapped and gapless spaces with any categorical symmetry S. The SymTFT gives us many predictions on ground state degeneracy, symmetry breaking properties, string and local order parameters, gapless phases. It enables us to construct a phase diagram and identify intrinsically gapless phases. And all of these predictions can be explicitly verified in lattice models, some of which are even suitable for practical implementation in quantum simulators based on cold atoms. So we've gone from categories to cold atoms. Now, I just want to comment that the SymTFT is also very powerful in higher dimensions. I've in particular worked also on 2+1D and in many different contexts, as we're hearing in this conference. So thank you very much.
Do you have some intuition for this? You had this slide with the interactions between the Rydberg atoms, and you said like there was particular radii you chose. Do you have some intuition for why those radii? And maybe a companion question is that setup particular to trying to simulate these REBD8 systems, or is that a more general setup that you want to use for anything else, or is it using the symmetry structure?
This setup is based on REBD8 because we have these 3 qubits on each side. And for this REBD8, for the D8 category, we input here in the SymTFT. So the radius here is to enable basically here interactions which are on this site I, whereas this one is between sites, neighboring sites I and I+1. So in particular, this is an asymmetric Rydberg blockade because these have 2 different radii. Right.
But just from the form of the interactions you want, is that clear why you want it like this, or?
Yeah, because in the Hamiltonians here, we have a term which is on the site I, which is given by projectors on site I, and another term which is between sites I and I+1, this interaction term. So here in this simulation of the experiment, this experiment with the measurements, first we apply the truly on-site operators, so on site I and also on each sub-site, 1, 2, 3. Then we apply these blue interaction terms for these Rydberg atoms all at the same site I, but on different sub-sites. And then finally we apply these inter-site interactions between, as I said, I and I+1, and then I and I-1. So this is in 2 steps. So yes, this is I think this setup of having this form of the Hamiltonian can be written for any REPG symmetry. So with the projector onto this subgroup F and then the interaction, these disordering terms within F. But this is general, this is for any REPG symmetry. The fact that here we have 3 qubits is specific instead to REPD8, but I think, it can be generalized, this setup.
For the intrinsically gapless SPT, you showed this interface, and there was an emergent anomaly with the Z2 symmetry after. I was wondering if you had any intuition for these intrinsically gapless SPTs for generalized symmetries. Is there always an emergent anomaly?
I'm not sure, I don't know. So in this case there is, but I don't know in general, sorry. No, I mean, for the group theoretical symmetry, yes, but for example, you could have that, I mean, basically, an intrinsically gapless space has symmetry properties which are not present in the gapped spaces it can be deformed to. So obviously, if we choose the group theoretical symmetry, which an SPT for the group symmetry for VecG, and then here we have an anomaly, basically we can't go to an SPT, a gapped SPT, because of the anomaly. That's for VecG. But for RecG, it's possible, in my opinion, that we could have a gapless phase which preserves this RecG symmetry, but which can't go to an analogous RecG SPT. So I don't think it's. Yes. Okay.
If you have more,
Okay.
okay, sorry. I think if you have IGSPTs, you have one vacuum.
Yeah.
By
Okay,
definition,
so
you have an anomaly. You don't have
must have the
hyperfactor.
anomaly, because otherwise we could always have one vacuum.
For if you have spontaneous breaking and gapless stuff, then I don't know. But if you have one vacuum.
Okay.
Sorry, so I thought that the definition was purely in terms of the Hasse diagram.
Yes.
So Christian, you're saying that there's some corollary of that definition that you can show that there has to be an emergent anomaly? I see. Okay.
Maybe I just want to follow up on Ruben's question. So suppose I had an arbitrary Hamiltonian with two-body interactions. Would this setup also work, or was there something specific about this that made it nice for the implementation of this Hamiltonian you're studying?
Okay. Yeah, so with this specific setup, which is quite simple, it's easy to induce interactions between this qubit at site 1 and the ones at site 2, or between 1 and site 3 here. So, for example, I mean, and that's why it's easy to simulate the first 5 Hamiltonians in our paper, but not the other ones, because this depends on the fact that we have this one qubit here in the middle driving these interactions. So there is actually, in the appendix of our paper, a proposed generalization of this to realize all directly 8 Hamiltonians, and which I think can be applicable to more general settings. But with this specific setup, it's easy to, since we have this one qubit here, which this introduces these interactions between the other two.
Yes, I understand, but suppose you had some other Hamiltonian, not related to RepD8,
yes,
but involve like couplings between these atoms like this. Does this setup would also work?
Yes, it would.
So it's not specific to this Hamiltonian, but.
No, exactly. As I was saying, like this basically, the setup depends on the fact that we have these local projector terms on the site and the interaction terms. So it doesn't depend on RepD8, but this is based on qubits. Okay, so it's generalizable to settings where we still have qubits. Or so I'm not very familiar with the state-of-the-art experimental setups, but I've heard of places where they can also do qubits and things.
Okay. And just another quick question. For the simulation, are you planning to initialize the ground state, or maybe starts with some?
Yeah, so actually this simulation is exact diagonalization. Mm-hmm. So what I did is I just wrote the Hamiltonian for the starting gapped Hamiltonian from that explicit expression here. And then I interpolated between the Hamiltonian for the Z2, Z2.
No, I meant the actual implementation in the device.
Oh, the actual experimental one.
What initial state are you planning to use?
Okay, so the trivial RepD8. So, for example, the easiest one is this trivial SPT. Obviously, because it just has these projectors. So we can easily study transitions, for example, from this trivial SPT to that SSB, which breaks the two-dimensional era. Yeah, see, so we can study transitions from this one to this one, for example, this is discussed in our paper, also the simulation. Or also, for example, between this and a non-trivial SPT. So this is another transition which we discussed and which is simulated in our paper, which can potentially be realized because you start with the trivial phase. So I think, yeah, the easiest ones are the ones where you start with this trivial SPT.
And then you want to adiabatically go to...
Yes, exactly.
Okay.
I think I'm following up on Nat's question a little bit. If we impose some additional interactions inside there, actually, backtracking a little bit, does the type binding chain over there actually commute with each other? I think if we want trotter to work in C, then I think the necessary condition is that you need a separable Hamiltonian which commutes with each other.
Yeah, exactly. A commuting projector Hamiltonian.
Yes.
Yes, this is crucial, that we have a commuting projector Hamiltonian. Indeed, because first we applied this projector term, and then we applied the interaction term, and since it mutually commutes with the projector,
so
it doesn't disorder
I
our
understand.
state. Yeah, exactly.
So
Thank you,
even
but
if we
yes,
introduce additional interaction terms inside there, if we project it and make them all commute, then the formalism will still be okay.
Yes.
Okay. Just a follow-up, that is first order trotter, isn't it? It's a first order trotter. There's a recursive formula which does second order and fourth order trotters, but the computational costs go up as it does by.
So, I mean, I'm a theorist, so you should ask.
Okay. Okay, thanks.
Yeah, thanks for the questions.
And for the gapless SPT, does the SymTFT picture give you any insight into the edge mode of the gapless chain, so the 0 plus 1D?
Yeah, Sakura and collaborators wrote a paper on the SymTFT with boundaries, and Christian wrote a paper on this boundary SymTFT. Yeah, so the SymTFT can also give insights on boundary modes, where basically one then fixes a module category at the edges. Yeah. But we haven't applied it to this case.
Okay, in this case. Thanks.
Okay, if there are no other questions, let's thank Alison.